Woeker, Wakker, Weet is 'n potsending vir wiskundeonderwysers, met trots aangebied deur die Vereniging vir Afrikaanse Wiskundeonderwysers, die VAW. Die potsending mik daartoe om al die kolle te verbind tussen literatuur en die praktyk, om so die wiskundeonderwyser te inspireer en te bemagtig. Juis sodat ons as wiskundeonderwysers kan voortbou op die wêreldklas onderwyspraktyke waarmee ons reeds besig is. Die internet gaan dit moontlik maak om die wêreld te reis in gemak. Ons gaan luister na skrywers, akademici en onderwysers. Daar gaan selfs 'n paar onverwagte gesprekke opduik. So sit agteroor en geniet die reis saam met my, Johan. Totsiens.
Well, g'day.
Hey James, how are you?
I'm doing well, thanks. How are you?
Awesome. I'm well. What time is it again now?
It's 8 a.m. in the morning, so we've obviously got our timing right. And what time is it for you?
5 p.m. So it's just at the end of my workday. For you, it's in the beginning of your workday.
Correct. Well, I hope this is a joyous end to your workday, or I'm not too much hard work.
I've been looking forward to this, and I have to go through several meetings just to end up here. So I'm happy. I'm very happy. Thank you.
Fabulous. Well done. Congratulations on a successful day then, and here we are.
Yes. All right, cool. So thank you for taking the time to doing this. I think I'm going to call it a podcast, but I'm not sure because it is something we share with the teachers just to start moving their minds in a different trajectory, because we've experienced that teachers get caught up in the day-to-day hustles, and then they don't take the time to listen to stuff like this or read. So we just want to package different ideas into short, let's call them podcast episodes, and share it with them, because that they can listen to on the way to work, etc.
Right, so it'll be purely audio, so you're not like videotaping this.
I am taping the video, but I don't think I'm going to use that a lot. But yeah, we'll see. I don't know.
Okay.
Yeah. So let's start.
I could have put on a better shirt or something, but
no, that's perfect. But just for interest sake, let's start. What I know about you is what I've seen on Twitter. So that's basically where I've started following you, and then
so you know me in 288 characters at a time.
Yeah. So it's most probably very skewed idea of you, or I don't know. But then
let's find out.
My previous boss, he introduced us via email, and then from there I just started chatting with you, and yes, you were very open, which is awesome. It's seldom that you see someone interested in maths and have this energetic persona around them. So I want to thank you.
I will tell you everything. No bars held. So it's going to happen. But also tell me about you a little bit. So what is this program? How long have you been established? And,
so
who is your audience typically?
We are a teachers, let's call it a teachers union, but not really, because we are not affiliated with the government or anything, but we look after the minority teachers that speaks Afrikaans, which is one of our 11 official languages. The government generally, when they do PD and give resources, it's always in English, because that's the one language that sort of covers most of the different groups in our country, because we are a very, very diverse country. So we are looking out for the minorities. Just to make sure that this language stays an academic language, the one that I speak as my mother tongue. And we want to preserve that. And the only way we can do that is if it's being taught at school level. And for that, our teachers need to be professionally developed constantly. So that is sort of where I come in. I'm the head of this union. We have roughly 1,600 math teachers.
Oh, wonderful.
From grades 4 to 12. I think you are based now in America, right?
Correct. I live in Phoenix, Arizona. Yep.
But you're an Aussie, I see on your Twitter.
I'm Australian. I'm in Tipperary like you guys. Yes.
Okay, cool. So so that will be years 4 to 12. Yeah, it's basically the same. Just on a tangent, do you watch rugby?
I'm afraid I don't. There's one reason I was booted out of Australia.
Okay, is that a one? Okay, because
there we go.
I don't usually get a lot of people that understand rugby, and when I speak to someone from New Zealand or Australia, that's sort of usually where we click. But Yeah, not with you
Unfortunately,
today.
no clicking on that front. I'm terrible. I'm terrible. It's the way I had to, like, that's the reason I had to leave. I was not living up the true Aussie way of following sports.
Okay, no, that's cool. So just in general, please tell the people that's going to listen to this your journey from basically your experience with maths as a kid,
Oh my goodness. All right.
and then jumping into your deciding what you're going to study, and then maybe your career path. But like summarize it, but you can take as much time as you want to.
This could be quite the story, because it is a story. Are you
Yes.
ready? Okay.
Yes, I'm ready.
So James Tanton's journey of mathematics through his career. He's currently 54 and all started, I guess, with schooling back in Australia where he grew up. So I grew up in Australia, Adelaide, Australia. And I have to say that my mathematics schooling was actually joyless. I did not like maths when I was in school, kindergarten all the way through. Now, don't get me wrong, I had fabulous teachers doing the right thing, but this is back in the 70s. And maths education in those days was very much memorize and do. It was a very rigid system. There's no, us kids were desperately asking, why do we need to know this? Why does this matter? Who cares? That was not the point. Our job was basically to take the information given to us, presented to us, told at us, and basically regurgitate it, which sounds very dramatic, but that's really was the message I got very early on as a child. I remember twice asking serious questions. I remember particular grade 5, year 5, we were learning long division, and I was fully cognizant. I had no idea why this method was working. We were told to do, write the big number under this funny symbol, the small number to the left, do this, all these weird subtractions and all the rest in the end. It made zero sense to me, and I was fully cognizant that that I was just doing this long division to actually please my teacher.
Yeah.
And I was not understanding why. And I was even labeled a gifted math student, which I thought was kind of silly because I knew I did not know what I was doing. I was simply pleasing the teacher. In year 9, I remember one of our teachers was teaching us the Pythagorean theorem. And please forgive me, I'm not being cruel to this particular teacher. It's the nature of the time and just dealing with 37 public school, high school students. I don't know how you deal with that myself. But the lesson began. Everyone gather your pencils and papers and rulers and protractors and draw yourself 3 examples of right triangles. Measure the 3 side lengths. Always call them A, B, and C. It just has to be those letters all the time.
In that
and
order.
Check. Work out A squared, work out B squared, work out C squared, and see if A squared plus B squared equals C squared. I had 2 problems with that. So I must have been a strange child. One, I don't believe anyone actually saw that A squared plus B squared equals C squared, because no one can actually measure perfectly. So I knew that was like probably close, but no one actually saw it. I let that slide. I let that point slide. The second point was that, how do you know it wasn't just a coincidence? It happened 111 times in a row. It just happened to work out. And I actually raised my hand and asked my teacher, sir, how do you know this wasn't just a coincidence that worked 111 times in a row? Each 37 kids each doing it 3 times.
Yeah.
And the response to me was really, really affecting. It was, go back and draw another 3 triangles. So I got the message for sure. I was not to know why the Pythagorean theorem was true, and it made me angry. Now, it could have shut me down, but didn't. It kind of spurred me on, actually. But I did actually, in my own reading and putting around, did figure out a proof of the Pythagorean theorem. I don't think I came up with my own proof, but I don't remember seeing one a few years later. Like, oh, fine, that's why it's true. But my mathematics experience really was joyless back in those days. I actually kind of left mathematics when I went to university. Not very far, I went to sciences. But I ended up taking some more maths courses. And it wasn't until I took a course in abstract algebra, group theory, ring theory, and all that sort of stuff in university. And everyone around me was just suffering because, like, this is so abstract. What is this about? But it just made me feel like, oh my goodness, I'm home. Because abstract algebra is all about, why does arithmetic work the way it does? It's the why questions, what if questions. It was the thing I've been yearning for 12 years as a kid and never had a tentative bet. I was pushed back for even wanting to know why. So then I realized, oh my goodness, I'm a mathematician. I'm a math thinker all along. And I went with maths all the way. So I changed my degree into getting a Bachelor of Science in mathematics. Even when I got my PhD, that's what lured me to America back in 1988, got my PhD in mathematics at Princeton. So I went all the way through with maths. So I just found that love, that passion, and it wasn't from my K through 12 experience. It was from later on. But then, being a very, timid sort of person, I followed the standard route. I then became a university faculty member. But I've always been interested in teaching. I actually chose, in America, they have these things called liberal arts colleges. These are university programs. They usually don't have PhDs and master programs, just an undergraduate program. But they have a strong focus on teaching as well as doing the research. And I wanted to make teaching a part of my life. I wanted to share the joy and passion of mathematics. But I only knew the university world, so I did that for a number of years. And then I met my fabulous wife, and we met in Maryland, and she decided to go back and get her PhD back at MIT. So we moved to Boston. And whilst in Boston, I somehow fell into doing a lot of professional development work with teachers, high school teachers. And I realized then I had no idea what I was talking about. I mean, I knew all the abstract mathematics, but I didn't know what was going on in high school mathematics at the time. So this is what, the late 90s. So I started looking at the curriculum in America in the late 90s. And I have to say I was gobsmacked because I just saw the same
thing as in the 70s.
joyless curriculum, memorize and do, as I had experienced some 20, 30 years ago in another country even. It was just joyless.
Yeah.
And that actually made me truly angry. And then I said to myself, okay, obviously there's something wrong here. I felt morally outraged by this, that if I really want to acknowledge that moral outrage, I have to try to do something about that personally. So I decided to leave the university world and become a teacher. And I thought about, okay, do I want to become what they call grade school in America, K through 6, or middle school, 6, 7, 8, or a high school teacher? And I looked at the curriculum, and I saw people doing good work in elementary schools, primary schools, and in middle schools. Don't get me wrong, they all needed some more help and fun, but I found high school particularly joyless, because I think there's a change of mindset, at least in this country, at least back in Australia, that the role of high school, it seems, in mathematics education is to get you into university.
Yeah.
Therefore, it's all about exams and getting high scores and moving you through. In which case, there's not much wiggle room for exploration, joy, creativity, innovation, play of ideas, asking the why questions, asking what if questions. Well, I did change the rules of arithmetic, will it still work? No time for that. Our job is to get you through those exams. So it became exam focused. So I decided to become a high school teacher in particular, because I thought it was the most joyous, most rigorous, rigid of all the arenas of education. I will tell you, high school teaching has been the hardest job of my life. Being a university professor is cushy compared to being a high school teacher. It is so frenetic. There is no time to think. I was teaching a full course load and doing all the extra stuff. And of all the arenas of education that gives teachers no room to contemplate their art and their practice, it's high school teaching, in fact, Kate's right, I'm sure as well, which to me is morally wrong. There's such an important arena of education. They're all equally important, but teachers give no mental space to reflect on their practice and try to do a refined and clever and innovative and meaningful job. Because the job is to get through exams. All right. So I looked for my wiggle room. Where could I actually teach the human story of mathematics, the human joy story of mathematics, and still get my kids to pass those exams? And there's things like this. I remember I was teaching an upper algebra class, and I had to teach my students how to divide polynomials. Why? I don't know. Why does everyone need to divide polynomials?
In the textbook.
Because in the and we've done that. It's part of the curriculum. Therefore, we do it.
Yeah.
Of course, students have every right to ask, why do we need to know this? And I would say, I don't know. As a research mathematician, do I ever divide polynomials? No. Could I figure it out if I had to? Yes. That's the key. I could figure it out if I had to.
Yes.
So I realized that the content is not important. In fact, I think you're kind of done with all the mathematics you need for everyday life if you just think that everyday life early on. High school mathematics is all for the advanced stuff, because the argument that people usually say is, well, why do this now? It's because you'll need to know it later on, which I think is a terrible argument. Either do it later on when you need it, or bring the later on stuff now that gives context to it. Do it now. It's just backwards in my mind. Anyhow. But I realized things like this. Polynomials. They are really an arithmetic system in base x rather than base 10. I mean, we humans are obsessed with the number 10 because we see our fingers on our hands all the time and think 10 is a very natural number for counting. But we even call our fingers digits, and we call the individual symbols in the number digits. That's not a coincidence. But, we did all polynomial work in base 10 back in grade 5. Well, we're just doing it in base x now. So I decided to give my students the story of place value, where I start at the very beginning. Let's assume we know nothing. Because I realized place value is a very subtle story, which is one of humankind's greatest achievements. The fact that we write numbers the way we do is actually stunning. And it took humankind thousands of years to come up with, which means it's not obvious. Therefore, it's ridiculous for us to think that third graders should have it under command and master place value. No, it's deeply subtle. So I decided, my high school students, we're going to examine place value. So we did that. We went all the way back to the very beginning. How do we write numbers? When I say 273, I literally say 200s. I said the word 100, 7T. Now in English, TY is short for 10. So we literally say 7 tens and 3. We spell it out. So I gave the story of place value, but not just base 10, but also base 2, base 3, base 1.5, all sorts of weird things. And by the way, just do it all bases at once. Don't know what to call that base number. I'll call it X. Everyone seems to call everything in algebra X. In which case, everything was like, well, polynomial division, piece of cake. So I was given 3 weeks to teach polynomial division or polynomial work, polynomial algebra. we were done in 3 lessons because we just realized we knew it all. But you can see it was just base 10. In fact, if you made x equal to 10, you really are doing, base 10 work. 2x squared plus 7x plus 6 divided by x plus 2 must equal 2x plus 3, because if you put x equals 10 and you're really doing 26 divided by 12 is 23, which I did back in grade 5. So just seeing those connections. So I realized that the power of high school mathematics is teaching the thinking and the joy of thinking and the power of self-agency and learning. And the content is not actually important. Content is the vehicle for teaching thinking. It's the vehicle for teaching thinking. Do I care about polynomial division? Not one whit. Will I teach it? Yes, because it's a powerful opportunity to teach thinking, not because I want my kids to be able to divide polynomials under speed, under a test, or what they have to, because that's just the nature of the curriculum, but it actually can teach wonderful life lessons. It gives you little problems and obstacles all the way. What do you do? Oh my goodness, this thing's not divisible by 3, that middle term. What can I do to make it divisible by 3? Well, maybe I need to add another x in the middle. Wouldn't that be nice? Can I just add another x? Well, you can if you think to subtract another x on the other side or something like that. It's a way to actually teach the power of problem solving. So I actually, yeah.
Sorry, so that is actually a common theme coming through these sessions that I have with people that have some experience with real maths, is the idea that schools actually only prepare learners for exams, because that's basically their mandate and that's what they get paid for, and that is what they are evaluated against. They, like my grade 5th year, 6th year math teacher, no one's going back to him and like congratulates him on giving me like the fire I have within myself of mathematics. He doesn't get a reward, he doesn't get a bonus, nothing, but he gets at the end of the year, when his classroom has a certain average, then he gets his applaud, etc. So if you train for the exam, you get what you as a teacher, with the assessments, like the assessments drive the way we teach. And
Yes.
just like before this podcast, I was in a webinar that was about level 4 questions. In our country, level 4 questions are open-ended, unfamiliar questions that kids, they cannot train for it. So it's very tough. And the whole idea was how to train kids for level 4 questions for examination purposes. and a lot of people were interested in this webinar, and I was saddened, and halfway through I walked out online, because I have the guts online to do that, but because it's so counterproductive. And then I came across this small book, and in Afrikaans it says like algebra for the final exam, and that is basically what all of these stuff in the general sense, when they do PD, when there's new books, etc., it's for examination purposes. And I feel that is killing the math curiosity within kids. Like I didn't have 90 and 100% whatever, but I always had this thing within me, why? And that's exactly what you said now. Why? And as long as you can ask why, even like I would get stuck at a question and not complete my question paper. And sometimes I would derive the formula, which if I only studied, then I could just use the formula. But then I had to derive it from first principles because I didn't memorize it. But that is fun. It doesn't give me marks. I failed a few tests until I learned to rig the system and play the system. And then you understand how the system works. But I think for the sake of marks and grades, I think you call it grades, like there's this false idea of a mathematician. It's usually girls, stereotypically, that can study really hard. In our country. In other countries it's Asian, or it's some group that studies really hard, does the procedures really good, memorizes the work very efficiently, get their 98, 99%, get accepted into engineering, some medicine or something. But at the end, they struggle because they don't ask why questions. And in those fields, you need people to ask why questions.
Well, who does Apple and Google and so forth hire? Not people that can answer previously answered textbook questions.
Exactly.
But people that actually ask new questions and make steps towards attending to them. I can't say answer them, but attend to them, make some progress forwards. No, you're absolutely right. If I was the lord of the entire math universe, the one thing I would change is the nature of assessment, because assessment actually dictates classroom experience and culture, and rightly so, rightly so. I mean, we say we value developing grit and perseverance and problem solving and creativity and innovation for our students, and we absolutely genuinely mean that. But if at the end of the day, if your measure of success is how well you do on an exam, then that's what actually counts. That's what counts. Doing exam scores count. In which case, if that is the defined measure of success, despite what we say and believe, then the best and most important and most intelligent strategy is memorize and do. Absolutely. And this works for students. I will never blame a student for asking me, will this be on the test? Because they've actually hit upon exactly the right strategy for that culture. Good for you. That's the right thing to ask for that culture. Now, I vehemently object to that culture, but that's the system, in which case, good for you, figured out the system. Same thing for educators, because you're right, at least in the US and other countries, often teachers' salary increases, or their jobs even, depend on students' test scores, in which case, the best and most intelligent strategy is teach to the test for your students. Then we do things like level 4 questions, and we just pull the rug out of under everyone's feet, because, hang on, you've been trained so perfectly to answer questions that have been previously answered, and now we're giving you something open-ended, and we're saying we value this, and we give it no opportunity to figure out even how to play with it. That's cruel. That is just cruel, in my opinion.
Last year,
what mathematics should be.
In our final exam, in our year 12 final exam, there was enough. So we have 2 papers, and generally the first paper is algebra, some calculus, some probability, and then the second paper is trigonometry and geometry. And they had an algebra question, but they graphed it. And there was a small protest because they included question paper 2 questions in paper 1. Because kids have been trained so well to answer algebra in a certain format that when you graph it, suddenly if you see a circle, you don't see x squared plus y squared plus z squared or whatever, but you see that in paper 2. But when it's in paper 1, you don't see it. It's not happening. It's not coming out because you've been trained. And that's problematic, especially I believe in this new industrial revolution that we go into in the 4th one, is if you, and you say it very well, if you can only answer previously answered questions, you'll be a very good Google search engine.
Yes.
But that's it. There's no creativity. Actually, I think, and I do believe research supports this, if you don't enhance and practice creative thinking when you're young, it sort of deteriorates. And then there's this time when it becomes obsolete and you just don't think creatively anymore.
I might even go a little further and say we've actually trained students out of it. I mean, a young toddler naturally asks why. Why to the extent that drives you batty as a parent, because why? And sometimes it's instinctual to ask why, but actually there's a level of curiosity there that we then, I think we take out of students. We train them to, you know, be quiet and be still and absorb and repeat. But if you think about it, what we're doing now is very, very strange. If I, as an adult person, want to work out 373 times 23, I'll pull out my smartphone. That's the best, smartest, most intelligent way as a citizen of the 21st century to answer that question. Now, should we not teach long multiplication? Well, if we're teaching long multiplication just to get answers with speed, then no, you take your smartphone. If the goal is to get the answer, we don't expect any shop clerk in their right mind when doing some problem, you know, on the shop floor.
We ask them not to do it.
Yeah, to pull out pencil and paper and do it by hand. We don't expect anyone in society to do it that way. Yet we still demand that our children learn long multiplication. I don't object to learning long multiplication, but what I would love to do, it has to be about the thinking process, the thinking about the structure, the numbers that's behind that. Sure, learn it. This is, again, another vehicle for teaching thinking. If you actually want to get the answer, pull out your smartphone, everyone. We are citizens of the 21st century. And students realize that too. And often you see a lot of, you know, algebra problems that are hokey beyond belief, trying to be real world problems like, you know, Sally bought 274 watermelons and 464 kiwi fruit at this. No one in the right mind buys 274 watermelons. So we train them to accept hokey problems and say that's real world maths. So no, I'm upfront and absolutely honest with my students, you know. If the goal is, in fact, I drove my department chair nutty. For example, I was given tests, little quizzes and so forth. You know, I don't know, what's the derivative of this or that or something, or what's the sign of some value. And I'd write in the margin all the answers to the problems. and still had big blank spaces. Because what I'm telling my students, I don't care what the answer is. I'll probably get it wrong myself. I'm going to make arithmetic mistakes left, right, and center. What's more interesting is the process to get to that answer. And actually, this worked out brilliantly well for two reasons. A, it gave some students emotional safety that they knew they're on the right track when they got the same answer to the numerical one.
Yeah.
And also, you know, it just also changed the mindset. I don't care. Show me how you get to the answer 2 pi plus 3 or whatever it is. That's much more interesting, and it worked very well.
I remember I went to the Netherlands in 2018 to the Utrecht University, and we had a discussion about open-ended problems. And that was the first time I was introduced to open-ended problems, because up until that point, maths was kind of a fixed subject for me, which if you follow it procedurally, you'll get to the right answer, and that's the game plan, and that's what you need to do. And I was working on this open-ended problem. I didn't know it was open-ended. They didn't tell us. And I was trying, and after the first iteration, I realized, but this solution can get better. And I did it again, and my answer was more efficient. I was like, what's going on here? And I changed some variables, and then I realized, wait, there's not a finite answer. And when I snapped that, then the facilitator, she knew this was the moment that she was working for in this whole thing. And she introduced me to open-ended problems. And she actually asked me, how did you feel? What did you experience? And that's the thing you want to evoke within the children. And I went back to school, and I was so amped. And I saw the kids, when I gave them these problems, and I experienced with them what I've experienced, this brief period of frustration, like extreme frustration. And then grit comes in. You grind through that frustration. You try different avenues, and that's problem solving. You contemplate with your peers. You get information. And then when you get the solution or a solution, and you have to defend that because the other groups have different answers. And in those arguments, in that communication, suddenly you fall in love with the experience of mathematical thinking. And it took time, but the lessons after that and the math that they actually learned within their discoveries, because not all the groups learned the same math, because some of them tried to solve this problem with, it was actually some sort of a quadratic pattern, but not everyone was on the level of identifying a quadratic pattern. So they had different approaches towards it. And I think that if we have more of these problems, and I think that is sort of what your site and everything you're working on, it's a big part of that, if I'm not mistaken, is introducing people to these problems, because good problems can actually make you fall in love with math. So, just chat further on that.
Sure. And in fact, listen to how you describe that. You could be describing some life problems like parenting for the first time. Well, what this is really teaching you is you've got a problem in your life. You're going to struggle with it. You're going to be frustrated. You're going to just have to take some first steps, get an answer. You'll consult with your colleagues, your fellow parents, or whatever your life problem is. You've just described the exact process we go through in dealing with a problem in life.
It's the same process.
A personal one, or for your family, or for your community, for the globe, whatever it is. I believe mathematics, because what you described is actually the perfect vehicle for teaching life skills, of actually taking agency, having the confidence to try something and just to do something and be your honest human self through it, because it's an emotional one. Mathematics is a human experience, therefore it's an emotional experience. And we seem to just strip it of all the emotion. You're meant to be speedy, fast, and right on the first try. That's the ideal, which is no humans that way. That's not human. No. In fact, mathematics took millennia to evolve in the way it has, and people struggle with it all the way through. It's not that nature. It's a human experience, therefore let it be one. In fact, I will openly, and I think you may have seen this in some of my material, talk about the first 2 key fundamental steps to solving a problem, which no one ever seems to talk about. You know, you've got some problem, be it like just even an exam question, or be it some open-ended problem, whatever. What have you got? Something thrown in front of you that you're meant to attend to. Step 1, be your honest human self and have an emotional reaction and acknowledge it. If the problem looks scary, be scared. Say, this is scary.
It's okay.
Flabbergasted, don't know what to do, gasp. If I say, oh, this looks cool, I'm interested, be interested. Just acknowledge whatever your emotional state is. Because people don't realize that you are a human being, have an emotional interaction with this problem. Step 2, take a deep breath and do something, anything. And I mean literally anything. Because most people shut down. When they have an emotional reaction, they shut down, feel like it's an impasse, and they can't move forward. Do something. And I mean literally anything. turn the page upside down, see what it looks like upside down, underline some words, draw a picture of a tree, draw a picture that might be relevant to the problem, put it aside and go for a walk for 10 minutes and let your subconscious mull on it. But that's the big thing. I wish we could do that in schools.
Yeah.
School is always busy work. Mathematicians are always going for walks and just letting subconscious mull on it. You know, if it takes me a day or a week or a month to have a first step, then it's going to take me a day, a week, or a month to have a first step. So be it. But school's all about instant do. No, put it aside, let your subconscious mull it. Because anytime you take some action, and if it's even relevant to the problem, you actually take a first step, and then you're on a path. And then it's easier to take a second step and take a next step. And then you actually start attending to the problem. But let it be a human experience. And we've stripped that humanality out of humanity out of it. Is the word.
I totally agree. Like, if I would usually, when I speak to my kids, I would take them on a journey and I would take them back in history. And I would tell them a story of where someone was confronted with a problem. And I had this one story that I read about the shepherd boy whose father had more than 5,000 sheep. And his father said that he is willing to pass it on to him if he can keep the same amount of sheep alive for 1 week. And that doesn't sound like a problem, but now it's the year 500 BC. So how do you keep track of 5,000 something sheep? What tools do you use? What number system do you live? Because this number system that we currently work with was not invented yet. And then the kids would be like, what do you mean invented yet? And you realize that maths is a language spoken by human beings. So like you said, it's a human experience. But because of, let's say, the media and the way we've commercialized maths, it seems like this analytical thing that's clear cut. And the people that do it usually is these emotionless, introverted people. They are speedy. And my boss always said, if a problem can be solved within 3 seconds, it's not worth the effort.
Well, first
then
of all,
it's not a problem.
If you solved it, it's just an exercise.
Exactly. So we are doing a lot of
speed multiplication. Good for you.
Yes.
Now, do you want to do another 150 or do some push-ups instead? What do you prefer?
And there is room for that, but that is not mathematics. Like my wife can do multiplication, but my wife is a nurse and she hates maths and she doesn't think problem solving. Like we are polar opposites.
She does. She's in a field that's full of problems and
but
innovation.
Okay, yeah, I stand corrected. You do problem solving. Yeah, I stand corrected. She does 100% of problem solving, but she doesn't use maths explicitly.
Right.
And what I would usually do is connect that to what she's done. Like if she, say for instance, they have to work out a roster at work and everyone has to work certain hours and it has to be the same amount within the week and everyone, that's a lot of math, but she does it with trial and error, etc. And then you see the patterns and then I notice it and then I can show her the math that she's actually doing, but she's totally unaware of it. Maybe that's maybe a better way of saying it. She's unaware of the fact that she's actually doing math. But yeah, so if we go on this narrative that math is a human experience and that lately in the last few hundred years, maybe we've taken that human experience away. We've substituted it with something procedural, mechanical, very clean.
Well, a focus on computation. It's really about computation.
Yes, that's most probably the biggest
mathematics.
So how do you go about bringing the human experience back and then qualifying it and actually telling the teachers, or how would you go about telling the teachers, please bring it back, whether it's going to be assessed or not? How can I, in a PD session, convince teachers to bring that back into the classroom, regardless of the fact that it's going to be assessed explicitly? It is going to benefit them in assessments, but not necessarily explicitly. Why should they bring it back? Because that's usually the debate I have, is the teachers will always say, but it's not examinable.
Right, so it's not an exam, therefore I don't actually have time to do that, and I so understand that pressure.
Yes.
So like I said earlier, so you think, why am I teaching my year 11, year 12 high school students about place value and what binary is, what base 10 is, and all the rest, when I'm meant to be teaching polynomial division? Because as I said earlier, I've had 3 weeks to do this whole polynomial algebra thing. I just gave the ground story of what this great invention of humankind called place value was. And then suddenly they realized, oh, it's just base X, it's the same as everything else. And we saved, literally we were done in three or four lessons, I remember. Add polynomials, no worries. It's like adding base 10, done. Actually going back and giving the full context to a math subject can save you time. If that's the goal, like I was worried, okay, this algebra unit has to be done in 3 weeks. Okay, we were done. And we played with other things and moved forward. It was grand. But that works all the way through because having the human story actually helps students understand its context and have it stick in their brains. For example, one of the cruelest things I think we do to students, at least in the US curriculum and in my curriculum too, I remember, was we have kids work in degrees all the way from when we first learn about angles in year 3, year 4, year 5, whatever, all through early high school. And then we get to pre-calculus, what they call it in the US typically. Oh, no, we'll just switch to radians. Yeah, we'll set to radians now. So we had you like work for 10 years of your life thinking degrees. Now we'll just switch because we do. Well, hang on. So let's think about why on earth do that. Mathematicians did that for a very human reason. In fact, even the number 360 is a very human reason. So start with the story. Who chose the number 360 for the count of degrees in a circle? It's kind of a weird number to pull out of the air. If I said to you, Johan, pick a number for the number of degrees in a circle that you think would be good for mankind, would you naturally say, oh, 360? Of course. Probably say 100 or something. I don't know what you'd say. It's kind of weird. So let's go back to the story. Who chose the count 360? And then you realize, well, what now human experience? In fact, should I give the little story about why? What?
Yes, please.
Here's the story. So you have to ask, well, okay, what now human experience has the number 360 associated with it? Why do we associate one full rotation, one full turn with 360? When you think about what us humans, well, we do experience one natural cycle in our lives as human beings on this planet, namely the number of days of a year. In fact, the Babylonians, 2000, 3000 BCE, knew that there were 365 and a quarter days in a year. Actually, they knew that wasn't quite right. So actually, when you think of the human year, you think, oh, let's associate the number 365 and a quarter with one full turn. And you say to yourself, who in their right minds wants to do maths with the number 365 and a quarter all the time? And then you say,
pre-calculator.
Yeah. So the natural thing is, what's the human thing to do? Round it, make it an easy number. So then you say, okay, if you had to choose what to round 365 and a quarter to, what would you round it to? A lot of people say 365, the nearest whole number. But some people say go to the nearest 10. And you think about it, oh, the nearest 10 is actually 370, not 360. So why did we go against the nearest 10 and went down to 360? And you think about this some more. Well, actually, think about it. You're human. You're doing back, 4,000 years ago, maths basically in your head. The number 370 is a bit awkward. I mean, number 360 is actually a bit nicer because you can divide 370 by 2. Okay, you divide 360 by 2. You also divide...
Mijn lijf is nogal tight. Maar ik moet zeggen, ze slaan die bal baie lekker. En het voel baie fris. Dus dis nie...
Okay, not sure what happened there.
You can divide 370 by 2. That was the last sentence I had.
And that's about it. I mean, you divide it by 5 and by 10 and by 37, but it's a very awkward number.
Yeah.
So it seems very natural and very human to want to go something that makes your life easy, go with 360. But then you ask yourself, okay, What would Martians do? Did they come up with the number 360 as well? No, not with 668 Martian days in a Martian year. So you realize 360 is a very human number. It's something we just happen to come up with because we happen to be on this particular planet revolving around the sun, which means it's actually very unnatural to the maths because it's a human reason we chose that number, not a math reason.
And there's actually error that we are actually not working with a minute doesn't actually have exactly 60 seconds. There's actually some stuff is more, but yeah. So for interest's sake, say for instance, a dictator somewhere on this planet of us, stand up, he conquers the world, and he decides a circle will have 942 degrees. And from there, he converts everything. That is totally plausible. He can decide that we work on a base 12 number system. He can decide that minutes has 6 seconds and seconds has 500 milliseconds. But then from there, everything just has to change accordingly.
So much of maths is social convention.
Yes.
Very human that way.
Yeah.
So then comes the question when you realize, oh, 360 is a human reason which happened to land upon that number, but it's very unnatural to maths. A more natural question would be, okay, I want to go one full turn. Let me just go around the simplest circle possible because I'm a human being. I like simplicity. So what's the simplest radius to choose? Choose 1. Let's just go with the simplest radius. If I walk around a circle of radius 1, how far have I actually walked? 2 pi times 1. 2 pi r is 1, 2 pi. Oh, let's call one full turn 2 pi. That's very natural to math. Suddenly there's a reason, like math kind of wants that to be the measure of one full turn. And then we realize we start doing advanced maths, like if you try to differentiate sine of x in degrees, you get this horrible factor of pi over 180 appearing, and it makes it horrible. Do it with x in radians, you get that the derivative of sine x is cosine of x. No weird factors appearing. So it's really much more natural to the maths. But the reason is because of that high level maths, when you start seeing this human error, this human sort of like perturbation come in and start to make things awkward.
But if we can remind and instill this idea that, or the fact that math is a human endeavor, then we actually tell the kids, you can explore it too.
Yes.
You don't have to wait for me to tell you what the answer is as a teacher. You can go and explore. Like the other day, I asked the teachers, is there something like square numbers in maths? And all of them said, yes, they know square numbers, 1, 4, 9, etc. So is there something like triangle numbers? And suddenly, only those who've studied some math that has triangle numbers and say yes. And the others was like, what? And then I would ask the obvious following question that a kid will ask, is there something like a rectangular number?
Yes.
And then all the other shapes. And then suddenly it becomes a very rich discussion. But because of the curriculum, as teachers, I think we also just limit our knowledge to what we need to successfully teach a kid for the exam. Like if a kid would ask me, why is a negative times a negative a positive? I don't think kids ask that anymore because it has become sort of like this common sense lingo.
Yeah.
You don't need to know why, it just is. And the teachers don't explore why because the kids don't ask why because they've been trained since grade 4 not to ask why.
So that's a very, very deep question, and negative numbers are extraordinarily hard. Humankind truly struggled with them all the way up to the 1800s. I kid you not, the 1800s.
But they're relatively new.
Right, they're very new. So like folks like Brahmagupta and what was he, 800s, 900s, and so forth, did actually talk about profit and debt. In fact, many cultures had profit and debt. So they did talk about, numbers for profit, numbers for debt. So there was a notion of negative numbers there. And they have a debt of 3 and a profit of 5. I'm basically up to. So people did think that way back in ancient China, back in ancient Egypt, and so forth. But then as a system of arithmetic, it was really Brahmagupta was the first to really sort of identify rules of arithmetic that might have these quantities called negative quantities, and wrote down rules like the product of 2 debts is a fortune. That is, the product of 2 negative numbers is a positive. What led him to that, I don't know. As far as I'm aware in the literature, he didn't explain why he would say that, but he just did, other than just seemed to make the arithmetic hang together. But people still call these numbers absurd numbers. Even the great mathematician Blaise Pascal, 1600s, called them absurd numbers. Many mathematicians through the Renaissance refused to work with them because they're just nonsense. They're actual nonsense. Even Euler had a hard time with them. The great mathematician in the 1700s had a really hard time with negative numbers, but he also tried to explain why negative is positive, and really came up with reasons, but they're like feel very forced. It wasn't until the 1800s that mathematicians realized, okay, what is going on? Back to the question of what makes arithmetic work the way it does. Now, the only numbers I feel we truly understand, or at least can have an intuitive feel for, are the counting numbers. 1, 2, 3, 4. I think that's it for us humans, is my personal thinking there. And we can do addition. Two apples and 3 apples, lump them together, 5 apples. We can think of multiplication, and in that context, it is repeated addition. Multiplication is repeated addition for counting numbers. So 2 times 3 is 2 lots of 3, or 2 groups of 3. I'm not sure what your country says, but 2 lots of 3, so 3 and a 3 makes 6, a repeated addition, which is fine. But if you look at all these notions of what you believe about addition, you say, but I'd also like to have anti-apples, please, coins and debt, whatever you want.
Yeah.
And I kind of still want those rules that feel so natural and right to me to still hold. Then there's going to be a game of just pure logical consequence. Okay, if you want, like your commutative property that 2 times 3 is the same as 3 times 2 to still hold, and you want that anything times 0 is 0 still hold, and you want to start playing with negative numbers as well, then it's one of the logical consequences, and it's only a logical consequence. It's not because I have a real world model for it, is that negative times negative has to be positive.
It's a logical consequence. I like the way you say that.
Yeah. And sure, every now and then it might appear as real world relevant, but that was not his motivation. In the end, it's because it's just, if you choose to play the game that arithmetic behaves the same way the counting numbers as it does, all arithmetic behaves the same way as the counting numbers, including the negative ones, then there's going to be consequences of making that choice. One is negative, positive. Now you can get at it. I mean, I can explain it to 5th graders, 5th year people. For example, to work out 17 times 18, I could draw a rectangle that's 17 long and 18 high, and chop it into 4 pieces, 10 and 7, 10 and 8. So I can see there's a little piece that's 10 by 10, 100. Another piece that's 7 by 10, 70. Another piece that's 10 by 8, 80. Another piece that's 7 times 8, 56. And so the answer is 306. But if you like to believe that negative numbers follow the same rules as every other number, then you can get quirky. Do the same thing and do not 17 as 10 and 7, do it as 20 and negative 3 on the side. And do 18 as 20 and negative 2. You've got this mysterious negative 2 times negative 3 in the corner, but you just know the answer has to be 306. That will show you have to say, in that corner, if I want to play the same game as I do with the counting numbers, negative 2 times negative 3 has to be positive 6. It's a logical consequence of the game we choose to play. Yeah. This is why I loved abstract algebra at my university. It's all about why do things work the way they do? Because we've settled on some basic beliefs about numbers modeled by the counting numbers, and we want to push them all the way through and find they're still logically consistent. It's actually good. It works out, which is lovely. It's amazing.
Yeah, usually when I speak to teachers and I would ask them, what do you love about maths? And then you have the 2 groups. And then the one group would say, because if you follow the steps, you'll get the answer. And they have this idea that math is just this pure elegant thing. And there's no human contamination into the subject. And which is far from wrong. If a different civilization, other than like the West did not discover maths, but they packaged it really well. And they sold it really well. The Arabic people, I think that's how you pronounce it, but they used the 10-digit decimal system.
Yes.
But they used it intuitively, and it had practical value. And then when they took it back to Europe and they sold it, suddenly it had value. But human beings decided, like in our country, in South Africa, we had the Khoisan people, which was the original indigenous people, and they have the oldest numbering system in the world, which is a binary numbering system. But so they only had 2 numbers. Later on, they evolved and they had 4 different numbers describing everything. So if they would conquer the world, say for instance, with ships, etc., but their math actually limited them to do that. But that's all discussion for another day. But if they did, and we would base the whole of civilization's math on the number system and the way that the Khoisan people did math, it would have been a totally different world. But the 10-digit, just the 10 digits, place value, multiplication, addition, that opened up a new world. A world where we could explore actually negative numbers, a world where we could explore imaginary numbers. It opened up a whole new world. And then I would ask the learners as well, do you think we are done with the number systems? Or are there number systems still waiting for us to be, and then this is my question, to be discovered or created by us to use? What would you say?
All right. So you got two very loaded questions there. All right. So let me give you one story about the number system. So in some sense, I can answer your first question definitively and also leave it open-ended. So let's go on a little journey here. So here's a little history lesson on this history of numbers as through the lens of solving equations. So the counting numbers 1, 2, 3, 4, 5, and so on are very good for solving some type of equations, like something plus 5 equals 11. You know the answer is a good whole number, 6. All right, so those types of equations, they're good at solving. But an equation like something plus 8 equals 5, counting numbers don't do it for you. You need a new type of number, -3, the negatives. Okay, we'll throw in the negative numbers now. So now we can solve those types of equations. And then, okay, great. So now I can solve things like 2 times x equals 8, or 5 times x equals -15. I can solve those, but I can't solve 5 times x equals 7. Bother. So I need a new type of number to be able to solve those types of equations. So we invent the fractions in this fictitious story I'm giving. All right, so now we've got the counting numbers, the negative numbers, and the fractions and all their negatives as well. Great. And we can solve some new types of equations like x squared equals 9 and x squared equals 16 ninths and so forth. But it was a real shock in 500 BC when the Pythagoreans discovered, Hippasus I believe it was, that x squared equals 2 doesn't have a solution amongst the fractions.
They didn't want to accept that.
And they struggled with that one. To give them a few more decades, they got there in the end. All right, so then, we need new types of numbers to solve other types of equations. So we invent the irrational numbers, like the real number system now. And that's great. Now we can solve x squared equals 2, but then people realize you can't solve x squared equals -1. So we invent another type of number system, the complex numbers, to solve those types of equations. But now you get worried. We start with the counting numbers, we can solve some equations, not all. So we invent negative numbers to solve more equations, but not all. So we invent, rational numbers to solve some equations, but not all. Irrational numbers to solve some equations, still not all. Will the story ever end? We have to keep on adding more and more number systems to be able to solve more and more types of equations. And here is one of the greatest surprises in the history of mathematics. In the year 1800, I believe it was Argand, managed to prove, in terms of polynomial equations, like basic algebra equations, the story stops there.
Okay,
with complex numbers, you can actually solve every possible type of algebra type equation, and it's called the fundamental theorem of algebra. It's called the fundamental theorem because it's the fundamental result. Algebra is done by the complex numbers. It's complete. It's packaged. Now, mathematicians still discover new types of numbers. If their context changes, it's not about solving equations. Then there was the Irish mathematician Hamilton who actually discovered quaternions. He was trying to understand rotations in three-dimensional space as their own number system, and found he couldn't do it in 3 dimensions. He could do it in 4 dimensions, which is kind of weird, and he invented a number system that actually described them beautifully. So they're not used for solving equations, they're for being applied to understand the geometry of space. Conway, in middle of last century, John Conway discovered these things called surreal numbers. He managed to find ways to put other numbers in between every pair of real numbers. Things that are smaller than every positive number, but not themselves 0. So this is like, we're going like weird world now. And you can imagine, for example, I could do the number that's 0.00000 forever, ... So infinitely many zeros, followed by a single 1. Now, that's so weird, but actually you can make sense of quantities like that, and that would be called a differential number, small hyperreal number or something like that. So you actually can invent other types of number systems if your context is different. Not about solving equations anymore, but if you like playing in other ways, yes. So yes, we can keep discovering new number systems.
So do you think we are discovering them or creating them? And the reason I'm asking that is the mindset idea between static and dynamic. Is there only a finite amount of math in the universe? Or as more problems arise, we can create new math as different contexts change, because math is a human endeavor and it's a language describing, in this is my definition, I've glued up with several other definitions, a language we use to describe phenomena that we see and experience. Math is not the phenomena itself, it just describes that. But we've made it so abstract that we sometimes see the math as the phenomena itself. But it's not, it's describing something that can actually be represented. I think there was math in the 50s that they declared this is rubbish, blah, 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 it's useless. And then within this 20th century, they discovered the actual use for that math.
So that's the paradox of mathematics. It's like a beautiful two-sided coin. It's actually motivates and creates real practical application. Like this is where most people think of math as they're saying, the applied side. It solves this practical problem. But it's the other side of the coin that's very abstract, poetic, beautiful, and just, you know, maths for its own sake, exploring and so on. So I actually believe maths is infinite. And especially because my slant is towards the poetic side of mathematics. If I write down the systems of rules that make the counting numbers work the way they do, instead of ring axioms, I can always tweak those rules in any way I like, and see if I can create another system that's consistent in its own right, which would be like brand new maths in some sense. But am I creating it? I don't feel like it. I actually feel like maths is already there. I think I'm discovering that. But there's infinitely many tweaks to be had. So there's so much to create, discover. I don't know what the word is. But then again, we're also biased. So in my childhood, I really was a math kid. I used to imagine what it'd be like to try to communicate with aliens. You know,
that's good.
Kids are always fascinated with intelligent life elsewhere. And I thought about this, and I actually had a very reasoned argument to myself. Okay, if I try to communicate with an alien, that means they must be aware of what communication is. That's the first thing I decided, which means they better be aware that there's of something other than themselves to communicate with. If they're not aware of other, then they can't communicate. If they're only aware of themselves, the whole issue is moot. In which case, so what I'm trying to communicate with must at least be aware of self and other. So at least aware of two states. And that made me think, okay, binary. I bet we could communicate with just two symbols. If they're aware of two states, maybe I have some hope of using two symbols, we have a way to communicate. What could I communicate? And I thought, well, all I could do is really possibly just take these two symbols and just blip out the sequence of prime numbers, the first million of them. Because that's probably not random. Anyone that gets the prime numbers is going to say, oh, that's coming from someone that's intelligent. So I decided that maths was the way that was going to be universal to communicate with any being that can communicate. Now, I was really shocked when I saw the book Contact by Carl Sagan later in my life and realized he had exactly the same idea. Let's beam a blip of the prime numbers out to space to see if everyone recognizes us intelligent. So I did the same thing as Carl Sagan did as a young lad, which is kind of great. But that points out my belief. I actually think maths is kind of universal, but I've left the door open. That was for beings that were aware of self and other. Now, there could be, as Douglas Adams says, intelligent shades of blue. They have no sense of other. And I'm sure there's probably a whole universe of way of thinking about maths that I can't even conceive of in my limited, biased view of what reality is. So
yeah, it's like
maybe
the book,
I don't know.
it's like the book Flatland, where all of these two-dimensional figures walk around and they're totally unaware of the third dimension. Where everything just appears for them two-dimensional. So that biasness is actually something that most probably is going to prevent us from discovering or creating new math. So the last thing sorry, what do you want to say?
But what I love about that is that here's the thing about maths. So as soon as you take it up to the third dimension, you can see what's going on, then everything suddenly seems obvious. So here's the humiliating thing about doing maths. Maths is like, nothing. You're stuck on a problem. You just know nothing. You're just stuck. You're just floundering. You're in complete dark. And as soon as that flash of insight comes, suddenly you have this major revelation. It's a rush. And they say, oh, of course. And then suddenly it just feels so obvious. It's like you don't even get the joy of
It's two states. It's two states. It's obvious and ignorance.
So when people say math is binary, it's not because you get the right answer. No, it's not binary in that sense. It's like, it's usually nothing, and then you know everything. And like, oh, okay, I should know that. Really. So, okay, which I love about maths. It's like you suddenly just see the third dimension, you realize, oh, if I only had just seen it in the first place, life would have been easier. Bingo.
I remember in my one algebra class, we did some coordinate planes. And up until that point, I only memorized everything theoretically. I had no practical example of all of these different polar coordinates, and there was different other coordinates as well. And then the teacher or the lecturer, he showed me a physical example of how coordinates work. And I'm ashamed of saying that, but it took me 19 years to just a simple bracket, say for instance, bracket X, Y, Z. Say for instance, it's 1, 3, 5. If you would take the room and you would make it the length, width, and height. And then he showed me you move 1 on the width, 3 on the breadth, and 5 on the height. And when I saw that, the whole of that course just fell into place. But it's such a simple thing that up until that point, I don't know why I've memorized that part of maths. I remember with transformations in high school, the teacher once explained, like if you rotate 90 degrees clockwise, this happens to the coordinates. And I had all of those stuff memorized,
Yes,
which is
yes.
quite a lot. And now I just visualize it, see it, look in what quadrant it is, and then know what's the values of the coordinates. But everything was dark, and then the light switched on, and that's exactly what you just told me. And that's experience worth fighting for. Whether it takes you 6 months and you have to endure 6 months of darkness, or 1 year, and actual mathematicians dedicate their lives towards a problem that they experience darkness, state of darkness, let's call it, or ignorance, or it's actually not ignorance. They're very intelligent, and then suddenly it just falls in place, and it's worth fighting for.
So that actually says a lot there, because it shows how easy it is for us to teach kids to do math. You did all those problems without having internalized.
And I got them right.
And yeah, you like me in my 5th grade doing all my long division problems. I got all the gold stars on those worksheets. I was like deemed like, here, this kid's got it. And I knew full well I had zero clue what I was doing. I was just performing. But it shows how easy it is for us to train kids to do maths. And what it also shows, it takes a very long time to internalize maths. Don't be ashamed of it taking 19 years or 9 years or 9 months, whatever it is. That's the nature of mathematics. It takes a long time to internalize it. And what you might take 19 years, it takes another person a day. It'll be a different story for the next topic in maths. It's all over the place. Some things are going to click for you right away because you have to be in the right frame of mind for that moment to have that intuitive feel for it. Other times you won't. Welcome to the human experience of math. It's organic, it's messy,
full of struggle.
And it can't really be placed on a schedule. Yeah, we teach it on a system that's nothing but schedule.
Yeah.
What a paradox.
Yeah, so hopefully some of the teachers, when they listen to this, they will feel inspired. And I think you also mentioned it when I taught, especially in the beginning of the year, it went really slow. But as we explored maths as a human endeavor, it sort of picked up pace, because suddenly the light switches just went on and the kids made the connections more frequently than not. But that is one of the things that as a teacher I instilled in the kids, is the absolute love for struggle. You have to, and struggle maybe is the wrong word, but you have to be willing to sit and fight with this thing, and then accept I've been defeated today, stand up, sleep, next day, fight it again. And have a battle with these ideas. Something that we don't have time for, and we have the excuse that we don't have time for.
So I was a very weird math teacher. So sometimes every now and then when we were stuck on a problem as a class, my homework that night, and I literally meant it, was your job tonight is to go for a 20-minute walk and not think about this problem. And
That's
next
brilliant.
day we'll come back to, and next day invariably someone had an insight that let us move this forward. Because that's what you do when you're stuck on a problem. Let it go and let your subconscious mull on it. Let's teach the life skill of what to do when you've got a problem.
Sleep on it. That is wisdom that has been given to us by our ancestors. Sleep on it.
Except for math class. No, don't do a math class. Come on.
You have to stay awake and work through the night. Let's finish off this discussion. It was really fun talking to you, because it's not a frequent experience when you talk to people about math and it actually feels like they are talking about music, or they're talking about poetry or
Thank you.
painting.
That's a compliment.
Yes, so it is extremely fun, and I think it is contagious. And I have experienced some change in some teachers, and if we can just change 5 classrooms where people think, maybe I should change my practice, I think I'm ready to die and move on to the next life. I will be happy.
But have your teachers be gentle on themselves. It's scary because we've all been trained in one particular mindset and culture of what this teaching gig is about. And change is fundamentally scary to us human beings. So take a micro baby step of something different. Try putting all the answers on your next test in the margin of the page and see how the kids react, and then have a discussion about it. And then maybe don't bother marking it,
that would be
whatever.
Brilliant.
Just try, just so what? Or try, actually, kiddos, tonight's homework really is to go for, we're stuck on this issue. Go for a 20-minute walk. Don't think about it. I mean it. You convince me you're doing 20 minutes of walking. Just mulling, just stroll.
That's what I
Yes,
like
right.
about the in our country now with the corona. The majority of our schools did flipped classrooms,
Yes.
and that works amazing because you go to your house. And you do the content, and when you come to school on your selected days, which is 2 times a week or maybe once a week, or you come and work on the problems, and that is so useful because now you come to class already engaged.
Yes. Yes.
And and for me, I think that is a positive thing out of the current pandemic that we experience.
Yes. I actually think there's a lot of good to come for it, because I think when we go back to our 4 classroom walls, no one wants to go back to the same old, same old. I think we've learnt there's actually more that we could do, and better and more joyous and more fun for student and teacher alike, actually.
I agree.
Yeah.
So let's close off with you telling us just quickly your projects that you run on. Let's not say advertisement, but you can, let's call it a short ad break.
Okay.
Please, just for the teachers that don't know.
Okay, so when I mentioned this thing about me teaching the story of place value to my upper high school kids, so we had to do polynomial division, it actually has become a bit of a global phenomenon. So I actually developed a story, something called exploding dots. And at this point, we brought this to the world. We created this thing called the GlobalMathProject, me and a few other fabulous colleagues, and just declared October 10th to be the start of Global Math Week. Why not? We chose the date October 10th because 10/10 is going to be read correctly no matter which country you're in, because in the US they read month then day, in Australia you read day then month.
Brilliant.
In South Africa, assume you do day and month, is that right? When you read 10/10,
I actually don't know. We do month and day.
You do? Oh, you do the US thing. Okay. You won't go wrong. 10/10 is the start of Global Math Week. And at this point, we've had over 6.25 million students and teachers across this planet just have an experience with exploding dots and talk about it. And I invite you to do it as well. Have your folks look at our website's about to be revamped. Give us a few days, but globalmathproject.org will give you all the material that came with that story about place value, that actually can take your students from just kindergarten math all the way to high school algebra, to college level math, and to some unsolved research problems still battling mathematicians today, all based on place value, the simple idea of place value. It is extraordinarily deep and rich and incredibly joyous, and apparently 6.25 million people on this planet seem to agree.
Amazing.
So feel free to have a look at it, check it out, and if you do something with your students during Global Math Week, if you just let me know about it, that'd be great.
Yeah, I think I will try and organize something. So I'll check your site and see what I can organize for our teachers. I'll maybe do a webinar with them where I explore it with them. That would be really cool.
Okay.
So then I'll tag you, and then when this podcast goes live, I'll also just tag you and tag the website. So when the teachers, so you are going to read some Afrikaans, you can just Google translate it.
I love it. I'd love to see it. Really.
The last thing I want you to criticize an idea I have. It's with my with my 4-year-old daughter. So I don't want them to learn maths remotely or rotely. Yes, I think that's the right
Remotely.
word.
Yeah.
Yes.
By memorization.
So, yeah, they can learn it remotely, but not rotely. So I had this game where I played with my fingers, and I would do this, and then I would tell my daughter.
That works well on a podcast, by the way.
Yeah, it does. Yeah, a podcast. Okay, let me explain. I would hold my 2 fingers up, and then when I slam my 2 hands against each other, the index finger of the one hand will move to the other hand, but in the other hand, obviously, it's a middle finger, not an index finger. And I would explain to her that we are doing addition. And then she can have like other fingers, and she actually believes she can do magic. So that's the cool thing.
That is magical. Come on, that's brilliant.
She believes this is magical, and it's sort of like a party trick when she meets new people. Like, see what I can do, and then she just the finger disappear. And then I would ask her, okay, so if you have 2 fingers on the one hand and 3 on the other, how would you do the trick? What? So she's exploring with addition, and then she runs into a trouble because if she has 4 on this hand and 4 on this hand, suddenly this trick doesn't work. And I just leave her there. Like, how is she going to figure this out?
Yes.
And then we can do subtraction as well. And hopefully she'll run into the problem subtracting 3 from 2. How am I going to represent that? And I'm waiting for the day where she has some form of representation for an addition more than 5 because she only has 5 fingers on one hand.
That is brilliant. And see, you could just tell her the answer and just denied her that ownership, that agency, that joy of discovering it for herself. And yes, there's a balance there of what one of my colleagues calls funstration. This can be fun for a while and frustrating.
Yeah.
But when it starts merging into frustration, then that's when
you have to step in.
us adults should need to step in and offer a little relief and nudge a direction of hope.
Because now currently she only limits herself to the problems that she can do with her hands.
She'll realize that. She'll realize that there's something deeper going on that's worth exploring and problematic. I love it. I think it's brilliant. So yes, full thumbs up. One on each hand smashed together should be 2 thumbs on one hand for you.
Thank you very much, James.
So then I'll leave you with a challenge. So you mentioned the triangular numbers and the square numbers. Well, I happen to personally love the number 36 because it's a square number. It's 6 times 6.
Yeah.
And it's also a triangular number. If you take 1 pebble, 2 pebbles, 3 pebbles, 4, 5, 6, 7, 8 pebbles, arrange them in rows, like a big triangle of pebbles, it's the 8th triangular number. So 36 is actually squangular. So here's both square and triangular.
Yeah.
I'd love to know if there are any other examples of squangular numbers.
Let me just write that down.
36 is both square and triangular. It's 6 times 6. And it's also 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. So pebbles can be arranged in a perfect square, or 36 pebbles can be arranged in a perfect equilateral triangle.
Okay, cool. That is very cool.
Grand.
Thank you very much, James. I enjoyed this.
This is a real
chat.
pleasure.
Thank you very much for taking the time. Okay.
My pleasure indeed. All right, be well.